Have you ever opened a bottle of nail polish remover? You know, the standard acetone one. Or maybe you've used a paint thinner for some project at home.
Oh, yes.
The moment you unscrew that cap, I feel two things happen instantly. First, that smell, it just hits you.
It's everywhere.
And second, if you spill even a tiny bit on the table or on your skin, it just vanishes. Poof.
And you feel that cooling sensation on your skin too, don't you?
Exactly. It feels freezing for a second.
That's because it's evaporating so fast, it's literally pulling the heat from your hand.
Which just makes you wonder, why? Why does this liquid disappear so much faster than, say, water?
Hmm.
A drop of water will sit there for ages. But acetone is just in such a hurry to leave. Why is that?
That is a brilliant question, and the answer, really, it lies in the invisible architecture of the molecules themselves. It's not magic at all. It's just chemistry.
Well, today we're going to find out exactly what's going on. Welcome to the Deep Dive. We're tackling Unit 8, aldehydes, ketones, and carboxylic acids. But we're zooming in on the physical properties of aldehydes and ketones.
And this is such an important topic. I think students often skip over it to get to the chemical reaction.
Yeah, the mechanisms.
But understanding these properties, it's the bridge between the structure you draw on paper and the actual behavior you see in a lab.
Yeah.
It explains why some things are great solvents and why other things smell so strong.
So we're going from why does it smell to how do I get full marks? I like that journey.
Yeah.
So let's start at ground zero. If I'm a student who just sees a bunch of C's, H's, and O's, how do I start to understand this?
Okay, let's break it down to the simplest possible level. The zero level, as we call it. Everything about the physical properties of aldehydes and ketones, their boiling point, their solubility, it all comes down to one key feature.
And that is?
The polarity of the carbonyl group, that C double bond O.
The CO group. Okay, let's unpack that. I remember from earlier lessons, carbon and oxygen are sharing electrons, but it's not an equal sharing, is it?
Not at all. Oxygen is much more electronegative. Think of it as being, well, very greedy for electrons. So it pulls that electron cloud towards itself. And what happens is the carbonyl group starts to act like a tiny magnet.
A magnet?
Yes. The oxygen end becomes slightly negative, and the carbon end becomes slightly positive.
Okay, I want everyone listening to try and picture this. Close your eyes for a second. Imagine that aldehyde or ketone molecule. It's not just a random shape. It's a tiny magnet with a positive and a negative pole.
Exactly. Now, imagine a whole beaker full of these tiny magnets. What are they going to do?
Yeah, opposites attract. The positive end of one will line up with the negative end of another.
Precisely. And that attraction is what we call a dipole interaction.
Dipole interaction.
Okay.
It sounds technical, but the magnet image really helps.
That's basically all it is. But, and this is the fascinating part, these magnets, they aren't super glued together.
Ah, so the attraction is there, but it's not permanent.
Correct. It's not a permanent lock.
So what's really happening between the molecules then? How does this stack up against something we know, like alcohol?
This is the key distinction. This is what you have to remember. Aldehydes and ketones have this dipole attraction.
Okay.
But they cannot form hydrogen bonds with each other.
Wait, hold on. This is a huge point of confusion. I've seen students make this mistake 100 times. They think, oh, there's an oxygen, so it must be hydrogen bonding.
Yes. That is the misunderstanding trigger line. It is the most common trap.
Right.
The rule is, to form a hydrogen bond with another molecule of the same type, you need a hydrogen atom bonded directly to a very electronegative atom, like oxygen.
So you need that OH group.
You need the OH group. Alcohols have it. But if you look at the structure of an aldehyde or a ketone, they have the CO group. They have the oxygen.
But no hydrogen attached to it.
Exactly. So they can't form those hydrogen bonds among themselves. They only have the weaker dipole attraction.
Weaker than hydrogen bonds.
Weaker than hydrogen bonds, yes. But stronger than the very weak London forces you find in simple hydrocarbons.
Okay, so there's a ranking here. Hydrocarbons are weakest, alcohols are strongest, and aldehydes and ketones are stuck in the middle.
In the middle, they're intermediate. So here is your insert safe definition that ties this all together.
Okay, let's hear it.
Physical properties of aldehydes and ketones are determined by the polarity of the CO group and intermolecular forces, specifically dipole interactions. This results in intermediate boiling points and moderate solubility in water compared to alcohols and hydrocarbons.
Intermediate boiling points, moderate solubility. That feels like the key phrase.
It is.
Let's create a mental movie for this. I want this to really stick. Let's go back to that beaker of acetone we started with.
Right, let's do it. Picture that liquid acetone. You have millions of these tiny CO magnets swimming around,
Right.
and they're trying to line up positive carbon to negative oxygen. There's a definite attraction holding them all together in the liquid state.
Okay, I see them clinging to each other, but now let's add some energy. Let's say it's just room temperature.
Right. That temperature is thermal energy. It makes all the molecules vibrate and jiggle around.
Okay.
And because that magnet attraction, that dipole force, isn't super strong, it doesn't take much energy for a molecule to break free.
It just wiggles hard enough and snaps the connection.
It does. It wiggles, the attraction breaks, and zoom. It flies off as a gas.
And that's evaporation. That's why the acetone disappears from the table so fast.
That's volatility.
Yeah.
And it's also why you can smell it so easily.
Uh.
The smell is literally those molecules escaping the liquid and flying into your nose.
The forces just aren't strong enough to hold them down. That makes perfect sense. You know, another analogy might help here, the social interactions one. I think it really clarifies this intermediate idea.
Yes, that's a great one. So think of hydrocarbons, like butane in a lighter. They are like total strangers on a busy street.
Okay, strangers.
They just ignore each other. Almost no attraction. So it takes very little energy to separate them, which is why they are gases. They have very low boiling points.
Right. So what about our aldehydes and ketones?
They're like moderately friendly acquaintances. They'll stop, say hello, maybe a quick handshake. There's a connection.
An attraction.
Yes. So it takes a bit more energy to pull them apart than the strangers. Their boiling points are higher.
And the alcohols?
The alcohols are best friends holding hands tightly. Or maybe a rugby team locked in a scrum.
Uh-huh. Okay.
They're held together by strong hydrogen bonds. You need to put in a lot of energy, a lot of heat, to break that grip. That's why they have such high boiling points.
Strangers, acquaintances, best friends, hydrocarbons, aldehydes, alcohols. That's a fantastic way to remember it.
And this concept is so important. Without it, we couldn't predict anything. We wouldn't understand why acetone is such a good solvent, or why formaldehyde dissolves in water to make formalin for preserving specimens.
Let's talk about that, the solubility. We said they can't hydrogen bond with each other, but what happens if you put them in water?
This is where it's very interesting. Aldehydes and ketones may not be able to form hydrogen bonds themselves, but they can accept them.
What do you mean, accept them?
Think about it. The oxygen in the CO group is slightly negative. Water has a slightly positive hydrogen.
So, the water can form a hydrogen bond to the aldehyde.
Exactly. The oxygen on the aldehyde can accept a hydrogen bond from a water molecule. And this is what makes the smaller ones soluble in water.
But you said the smaller one, so there's a catch.
There's always a catch in chemistry.
I knew it.
The catch is the rest of the molecule. That carbon chain, the nonpolar tail.
Okay.
As that tail gets longer and longer, it's hydrophobic. It hates water. So for small molecules like formaldehyde, the polar CO headwinds and it dissolves.
But for bigger ones?
For bigger ones, the long, oily tail gets in the way and pushes the water molecules away, so solubility drops off very quickly.
Got it. So the hydrophobic tail just overpowers the polar head.
Perfectly put.
Okay, let's tie this to a few more real-world examples. We started with nail polish remover.
Acetone, yes. It's used because it's in that perfect zone. Its polarity is strong enough to dissolve the polar chemicals in the nail polish.
Okay, so it does the cleaning job.
But its own intermolecular forces are weak enough that it evaporates really quickly, leaving the nail dry. It's the perfect balance.
Sticky enough to dissolve, but loose enough to fly away.
That's brilliant. I'm going to use that. Loose enough to fly away.
Okay, now for a counterintuitive one. A question that always trips students up.
Go on.
You might think, since aldehydes and alcohols both have oxygen, their boiling point should be similar, right?
That is the naive assumption. But actually, when you look at the numbers, it's a completely different story.
Let's compare them.
Okay? Take ethanol and alcohol. Its boiling point is 78 degrees Celsius.
78. Okay.
Now take acetaldehyde, an aldehyde with a very similar molecular mass. Its boiling point is just 21 degrees Celsius.
Wow. 21, from 78 down to 21.
It's a massive drop.
That's huge.
It really shows you the raw power of hydrogen bonding. That 50-plus degree difference is purely the energy needed to break those best friend handholds in the alcohol.
That puts it all into perspective. Okay, this is super clear. Now, for everyone listening who's preparing for exams, we need the money lines, the sentences that get you the marks.
Absolutely. Precision is key in an exam. So let's go through the 4 clarity lines you need to know.
I'm ready. Clarity line number 1.
Aldehydes and ketones have higher boiling points than hydrocarbons of similar molecular mass.
And the tieback is?
This is important because of the dipole and dipole interactions from the polar carbonyl group.
Got it. Clarity line 2.
Aldehydes and ketones have lower boiling points than alcohols of similar molecular mass.
And the reason is critical here.
Do not confuse this. It is because they cannot form hydrogen bonds with themselves.
Perfect. Clarity line 3.
Aldehydes and ketones are moderately soluble in water
And why is that?
because while they don't H-bond with each other, they can accept hydrogen bonds from water molecules.
Right. And the final one, clarity line 4.
As the carbon chain gets longer, solubility decreases.
Because that nonpolar tail gets too big and interferes.
You've got it. Write those 4 points, and you're safe.
Fantastic. Okay, let's wrap this up with a quick summary. What have we learned today?
We've learned that it all starts with the polar CO group. This turns the molecules into tiny magnets.
And these magnets create dipole interactions, making them like acquaintances, stronger than stranger hydrocarbons, but weaker than best friend alcohols.
Which gives us our boiling point order. Hydrocarbon is less than aldehyde ketone, which is less than alcohol.
And we learned that this explains why acetone is a great solvent that evaporates in a flash.
Exactly. It connects the drawing in your textbook to the smell of paint thinner in the real world.
Before we go, I want to leave you with one final thought. The next time you see a bottle of acetone, think about this. If it evaporates so fast because its molecules aren't holding on tight, just imagine how much energy is locked inside a simple cup of hot tea. All that heat is just fighting to keep those super strong H-bonded water molecules together.
It gives you a new appreciation for a simple cup of water, doesn't it?
It really does. And next time you smell something volatile in your house, that strong smell of a marker pen or a cleaning fluid,
Ask yourself.
is that an aldehyde or a ketone escaping?
It's chemistry in action, all around you.
It is. Unit 8 isn't so bad when you break it down. Thanks for listening to The Deep Dive.
Good luck with your studies. Keep asking why.